If cosmic expansion stops, the universe won't explode or implode. Instead, gravity would slowly reassert itself, reshaping cosmic motion. Think of galaxies like boats drifting apart on a calm ocean. So stopping expansion changes motion over billions of years. A deep, empty sky peppered with distant, faint galaxies. Stopping expansion means the scale factor stops increasing over time. In plain terms, space itself would cease stretching further. This matters because expansion sets the backdrop for all cosmic motion. Gravity would then act within a static stage, changing how structures evolve. Mechanically, individual distances stop growing unless local forces act, and gravity then operates against static space. For example, the Virgo cluster might slowly tighten over billions. Nearby galaxies once carried apart would experience much slower separation rates. Net picture: space stops stretching, and gravity wins locally. Start with grand scales where expansion currently dominates motion. On the largest scales, galaxies recede due to cosmic stretching. If expansion halts, that recession would stop gradually, not instantly. Photons already en route would remain redshifted by past expansion. New photons, however, would stop gaining extra stretching, changing future redshift trends. Large-scale flows could then reverse slowly, as gravitational attraction accumulates over time. For example, two superclusters separated by hundreds of millions light-years could eventually draw together. But this would take tens to hundreds of billions years. So the net result is slow rearrangement of cosmic structure over eons. Focus now on galaxies and their mutual gravitational dances. A galaxy is a bound collection of stars, dark matter, and gas. When space expands, galaxies in clusters remain bound by gravity. If expansion stops, those bound systems remain mostly unchanged at first. Unbound galaxies between clusters would cease drifting apart and could be drawn back. Mechanically, orbital energies shift as expansion no longer removes kinetic energy, changing orbital decay rates slowly. For example, the Milky Way and Andromeda will collide in about 4 billion years anyway. If expansion stopped, that timetable would not be delayed materially. So galaxy interactions would become more common over very long timescales. The cosmic microwave background is a fossil light bath seen everywhere. It was stretched by expansion, cooling as its wavelengths grew longer. If expansion halts, new photons will no longer be stretched further, altering future cooling trends. That matters because the CMB sets a thermal floor across the universe. Mechanically, photon energy loss from stretching ceases, so the CMB temperature could asymptote. For example, instead of cooling indefinitely, the CMB might approach a near-constant temperature at very late times. This would subtly change chemistry in diffuse regions and structure timing at the margins. Net result: background evolution alters quietly, not catastrophically for observers. Local physics inside galaxies changes far less than cosmic scales. Stars keep burning under nuclear fusion, unaffected immediately by expansion changes. Planets remain bound to their stars, and climates stay dominated by starlight. Habitability depends on local energy budgets, not cosmic expansion directly. Mechanically, only very long-term changes in interstellar density would affect systems. If galaxy mergers rise, star formation could increase temporarily, and supernova rates could climb. For example, Earth would still orbit the Sun exactly as today for billions more years. So life on planets experiences little immediate impact from expansion halting. Bottom line, local habitability stays robust for very long times. Cosmologists worry about three broad fates for the universe. If expansion stops, one possibility is a static balance briefly maintained. Another possibility is eventual recollapse, where gravity overcomes inertia fully. A third possibility is a new equilibrium, where expansion neither grows nor shrinks. Which outcome depends on dark energy's true nature and overall matter density. Mechanically, if dark energy decays, gravity can pull space back inward, starting collapse. For example, a gentle decay could produce a recollapse across trillions of years. Net result: stopping expansion opens multiple long-term cosmic scenarios. Detecting a halt requires precise cosmological measurements across time. We measure expansion using supernovae, galaxy surveys, and background light. If expansion slows, observed redshifts would deviate from expected trends. Mechanically, surveys compare distance indicators across billions of years look-back. We would also track growth rates of structure with weak lensing and clustering statistics. Instruments like JWST, Euclid, and large ground telescopes play key roles. For example, a consistent slowdown would appear in standard candles and lensing maps. So the observational challenge is long-time baselines and exquisite precision. So if expansion stopped, gravity would quietly reshape the cosmos. Changes unfold over billions to trillions of patient years. Local systems like galaxies and planets remain largely safe for now. Big shifts depend on dark energy, which remains mysterious and crucial. If you enjoyed this cosmic thought experiment, consider exploring more. Subscribe for gentle deep dives and occasional wild cosmic questions. Thanks for watching, and see you in the next Curiosity Burst.